Today we are going to discuss about cubic spline once again. In a previous lecture we discussed about how we fit a cubic spline function using a direct method. There is a since direct method is a very lengthy approach, so there is another alternate approach to fit a cubic spline function. So here in this lecture we are going to discuss about that alternate approach. So first we give the brief introduction of our cubic spline, then we derive the alternate approach, means how we fit a cubic spline function between any class interval. Then we solve one numerical example based on that alternate method. So as in a previous lecture we discussed about what is a cubic spline function. So here already we written this one. What is a cubic spline? A cubic spline is fx, a function fx, satisfies the following properties for xi, I equals 0 to n, and corresponding values of a function is fi, means at xi the value is fi, at x0 the value is f0, means this pair of values is given x0, f0, x1, f1, xn, fn, satisfies these three properties. First one, the value of the cubic spline function equal to the value of a function for each data, means I equal to 0, f of x0 equal to f0. And second is fx is a cubic polynomial in each class interval. In each class interval means x0 to x1 there is one polynomial, a polynomial of a degree 3, and x1 to x2 another polynomial, similarly xn minus 1 to xn another polynomial. And third one is a cubic spline function, their derivative, first derivative, their second derivative is continuous for I equal 1 to n minus 1, means for internal nodes, the cubic spline function must be continuous. So this one is what? This one is a definition of a cubic spline function. So using this property, in alternate approach we use this property, means f double dash xi is a continuous on a internal nodes. So using this property we are going to derive a process how we find the unknown of means how we write a polynomial in a given class interval, and then how we find the unknown of a polynomial, means a polynomial of a degree 3, then how we find the unknowns, or how we write a polynomial. So as we discuss, cubic spline function have a property, means fx, f dash x and f double dash x is continuous at internal node. So we use this property. Suppose f double dash x is graphically we try to explore this one, means there are different points, means x0, x1 and here xn minus 1, and this one is a xn. There are n plus 1 nodes or n plus 1 nodes, and corresponding value of the function f0, and this is f1, and here there is fn minus 1, and here fn. And for sake of a simplicity here we write another point xi, and here the value is a f of xi, and if we follow a similar notation we may write this one is a fi, and before xi there is a xi minus 1, and that function is a fi minus 1, and after xi another node xi plus 1, and value of the function is fi plus 1. If I ranges from what? I ranges from 1 to n, then x ranges from x0 to xn. So, what's happened in alternate approach, we fit since f double dash x is a what? F double dash x is continuous between continuous at internal nodes. So, what is the nature of a curve f double dash x? Here we know that fx is a cubic polynomial. Fx is a cubic polynomial. Then what will happen? F dash x become the quadratic polynomial. Similarly, what will happen with the, if we differentiate once again, then f double dash x is polynomial of degree 1. Polynomial of degree 1. Obviously, if fx, capital Fx be a cubic x-spline function, means we try to fit a cubic polynomial, then f double dash x is a linear function or polynomial of a degree 1. So, we use this property and we try to fit f double dash x as a polynomial of a degree 1 with the help of a Lagrange interpolation formula. So, we try to fit f double dash x is linear function between xi minus 1 to xi. Is a linear, we assume that arbitrarily we take a class interval xi minus 1 to xi. If the value of I is a 1, then this become x0 to x1. If I is a 1, x0 to x1, I is a 2, then x1 to x2, x2 to x3, x3 to x4, and similarly xn minus 1 to xn. So, as we know that how we fit a linear polynomial with the help of a Lagrange function, we use the Lagrange interpolation formula. So, Lagrange interpolation formula for the two values, two ordinates, two nodal points are two nodes. So, for these 2 points, we write a Lagrange interpolation formula. Now by Lagrange's interpolation formula, interpolation formula f double dash x equal what? F double dash x equal here x minus xi divided by xi minus 1 minus xi into f of xi minus 1, or here we write f of I minus 1, because this one is a notation corresponding to xi minus 1. What is the value of the function? The value of the function is f of I minus 1 plus x minus xi minus 1 divided by xi minus 1 f of I. So, to make the denominator similar in both the term. Here we write f double dash x equal xi minus x divided by xi minus 1, means taking minus 1 from outside from the numerator and minus 1 from the denominator, then this become xi minus x divided by xi minus 1 f of I minus 1, sorry, not f of I minus 1, here fi minus 1 double dash, here fi double dash, the value of the function, the value of a second derivative at x equal xi minus 1, the value of a second derivative at x equal xi. So, this one, and here we write x minus xi minus 1 upon xi minus 1 fi double dash. For sake of a simplicity, here we write the denominator of both term have to be same. For sake of a simplicity only, you may start from this one also. And also for sake of a simplicity, here we use again one another notation, f double dash I minus 1 equal m I minus 1, and here we take a let f double dash I minus 1 equal m I minus 1 and f double dash I equal m I, capital M I. This one is a standard notation that most of the author follow this type of a notation. That is why here we write f double dash I minus 1 equal m I minus 1 and f double dash I equal m I. So, what will happen here, we write in a next phase. In a next phase we write f double dash x equal xi minus x upon xi minus x upon xi minus 1 m I minus 1 plus x minus xi minus 1 upon xi minus 1 mi. Since this one is a linear function, so in order to find out a cubic polynomial or in order to find out a fx, this one is a second derivative of a fx, so we integrate this function 2 times. So, if we integrate this one 2 times, integrating here, if we write this one is equation number 1, integrating equation 1 2 times, then what will happen? Obviously, if this one is a second derivative, then we are able to find out the value of the function with two constant of integration. So, what is the value of integration? If we integrate this one 2 times, then what will happen here? F double dash x, and here for also a sake of a simplicity, we may write this one as a hi, means a length of a class interval. So, we may write this one as a hi. Here we write a hi, and also this one we write a what? We write a hi. Hi is a constant. This one is a length of a two successive nodes, because nodes is also known as a knots. So, xi minus 1 is denoted by the hi, and xi minus 1 is also denoted by the hi. So, what is the value of integration? The value of integration is a what? The value of integration, if we integrate 2 times, this become xi minus x whole cube divided by what? Divided by 6 hi. 6 hi, because if we integrate one time, then xi minus x xi whole square of xi minus x divided by 2, then we integrate second time, then this one give the xi minus x whole cube divided by 6 into hi. Minus 1 first time, minus 1 second time, then this become 1. So this one is a value of integration of a first term with what? With multiple of mi minus 1, and similarly if we integrate the second term, then 2 time, then this become x minus xi minus 1 whole cube divided by 6 hi into mi plus c1x plus c2. First time if we integrate, then this one is a c1, second time if we integrate, then c1 x plus c2. This one is a value of integration. This one is not a f double dash x now, because if we integrate 2 times this function f double dash x, then this become what? This become fx, and this one is a linear function. Obviously f double dash x is a linear function, as we said earlier. F double dash x is a linear function that we fit with the help of a Lagrange interpolation formula, and if we integrate 2 times, then fx is a what? Fx is a cubic polynomial. Cubic polynomial. And what is the value for in which class interval? If we try to write here, x lie between xi minus 1 to xi, and I ranges from 1 to n. If I equal 1, then this one is a cubic function from x0 to x1. If I equal to 2, then this fx give this expression give the cubic polynomial for the second class interval. Similarly, if we put I equal to 3, then we find the cubic polynomial for the third class interval, similarly for the nth class interval. But what is the unknown here? Unknown is the what? Mi minus 1, mi, and c1 and c2. So first of all, we try to find out the value of a c1 and c2. C1 and c2, we try to find out the value of a c1 and c2. We try to find out the value of a c1 and c2. Now how we find the value of a c1 and c2? We know that the value of the function at x equal xi means we know that f of xi equal to what? Fi, and f of xi minus 1 equal to also what? Fi minus 1. So here what? In this expression, once we put x equal xi and putting the value equal to fi, and again put x equal xi minus 1 and putting the value f of xi minus equal fi minus 1, then we get two equation with two unknowns in term of mi minus 1, mi, fi, and fi minus 1. Then we solve that equation in order to find out the values of c1 and c2. So here we write once we put x equal xi here, if we denote, this one is equation number 2. This one is equation number 2. So next we are going to find out the value of a c1 and c2. This one give the fx, capital Fx, for each class interval x0 to x1, x1 to x2, and xn minus 1 to xn, xn minus 1 to xn, and each polynomial with the order of each polynomial is a polynomial of order degree 3. Means fx is a polynomial of a degree 3 for each class interval. Now how we find the value of a c1 and c2? As we say that we put x equal xi in equation number 2 and x equal xi minus 1 in equation number 2 again, then we try to find out the values of unknowns. So what is the value of unknown? The value of unknown, how we find? If we put x equal xi, then f of xi equal to Fi, and right hand side become what? Right hand side become, first term become xi minus xi divided by hi mi minus 1, means if we put x equal xi here, then this term becomes 0. Okay. So, whole cube, this term becomes 0, plus second term become xi minus 1 whole cube, this one is a 6 hi, sorry, upon 6 hi mi plus c1 xi plus c2, c1 xi plus c2. Similarly, if we put x equal xi minus 1, then this one give the f of xi minus 1 equal fi minus 1, this one equal to xi minus 1 upon 6 hi, means here we put what? Here we put x equal xi minus 1, then this become xi minus 1 upon 6 hi mi minus 1 whole cube, and second term become what? Second term become xi minus 1 minus xi minus 1 whole cube divided by 6 hi mi plus c1 xi minus 1 plus c2. So, as you see here, what is the value for this one? This become what? This term become 0, and this term in a second equation, this term become 0. This term becomes 0. So, what is the simplified form of equation? Fi equal first equation become xi minus xi minus 1 whole cube divided by 6h mi plus c1 xi plus c2, and second equation become fi minus 1 equal to, second term becomes 0, first term be the xi minus 1 whole cube divided by 6hi here, 6hi, and this one is a mi minus 1, and this is, sorry, not a mi minus 1, this one is a mi, and this one is a mi minus 1 plus c1 xi minus 1 plus c2. So, if we solve these two equations, equation number 3 and equation number 4 for c1 and c2, means if we subtract these two equations, then we are able to find out the value of a c1, and if we multiplied by the xi minus 1 in equation number 3rd and multiplied by xi in equation number 4, then after simplification is very easily be able to find out the value of a c1 and c2. So, if we solve this simultaneous equation, then be able to find out the value of a c1 and c2. So, directly here we write the value of a c1 and c2. So, this one is a what? This one is a value of a c1 and c2. This one is a c1, and this one is a c2. This one is a c1 and this one is a c2. After solving the simultaneous equation 3rd and 4th, we get a value of a c1 and c2. Once we put the value of a c1 and c2, then we find the value of a what? Then we find the value of a fx. So, what is the value of a fx? Now, fx become, now if here we write fx equal, first term be the xi minus x whole cube divided by xi minus x, or if we write in term of hi, then this becomes 6 hi mi minus 1 plus x minus xi minus 1 divided by xi, or you may write 6 hi in term of 6 hi plus c1x. Here we put the value of a c1. c1 is a what? fi minus 1 divided by hi plus hi by 6 inside mi minus 1 into c1x. So, this one c1x, then we write a c2 plus c2. c2 is 1 upon hi into xi fi minus 1 minus xi minus 1 fi minus 1 upon 6 or hi by 6 into xi mi minus 1 minus xi minus 1 mi. This one is a what? This one is a fx, and this one is a true for each class interval x lie between xi minus 1 to xi, and I ranges from, obviously I ranges from 1 to n. So, this one is a what? This one is a cubic spline function for each class interval. So, if we write this one in a simplified form here, mi is, I think mi is missing. So, here we write a mi. If we simplify this expression, then we may write this expression in this form also. This form means we arrange the term of xi minus x mi minus 1 at one place, mi at one place, and the coefficient of this one means hi x by 6 mi minus 1, this one is a one place, then we able to write in this form. We may also write this one in this form. If we simplify this expression, then this can be also written as 1 upon 6 hi inside xi minus x whole cube mi minus 1 plus x minus xi minus 1 whole cube mi. This is the first term. Second term is if we write 1 upon hi plus 1 upon hi inside, if we write this term is if we equate this term and this term, then this become xi minus x fi minus 1 plus x minus xi minus 1 fi. This one is the second term, and third term is a minus hi by 6. Hi by 6 means we equate this term and this term. Then we get minus hi by 6 xi minus x mi minus 1 plus x minus xi minus 1 fi, not fi, means mi. So, if we remember the formula of fx in this form, then it's become easy to remember, because xi minus x whole cube mi minus 1 x minus xi minus 1, there is a In each term there is a means a term of a what? Term of a xi minus x here, xi minus x here, xi minus x here, x minus xi minus 1, x minus xi minus 1, here mi minus 1, mi, fi, mi. So, in this form, if we remember the formula for fx in this form, then it's become very easy to remember the formula for fx. So, this one is a fx and this one is a true for x ranges from xi minus 1 to xi, I ranges from 1 to n. Now, what is the other things? There is just some unknowns, means we have a value of xi minus 1 and we have a value of fi minus 1, fi also, but we doesn't have the value of mi minus 1 and mi minus 1 and mi. Then how we find the values of mi minus 1 and mi? Then in order to find out the values of mi minus 1 and mi, we use the again one another property, means property of a cubic expline. F dash x is also a continuous at their internal nodes. F dash x is a continuous at their internal nodes. So, what is the meaning of this one? Means in order to find out the values of mi minus 1, we use the property, means f dash x, here we write f since f dash x is continuous at internal nodes. Suppose that internal node is one node is a xi. Let xi with the internal nodes. Then what will happen? If f dash x is a continuous, let xi with the internal node, internal node, then what will happen? F dash xi plus epsilon equal to f dash xi minus epsilon. If epsilon tends to 0, here epsilon tends to what? Epsilon tends to 0. So, in order to write this value of this function, value of f dash x at xi plus I and value of f dash x at xi minus epsilon, there is a need to value for f dash x for x lie between xi minus 1 to xi and f dash x at x greater than xi and less than xi plus 1. So, if we have a value at x equal xi in this class interval, then we put f dash xi here, f dash xi minus epsilon, then we put x equal xi minus epsilon in equation number, if we write this one is equation number 5, this one is equation number 6. So, if we put x equal xi minus epsilon, then we put here x equal xi minus epsilon. If we put x equal xi plus epsilon, then we put here. So, how we get the value of f dash xi plus epsilon, f dash xi minus epsilon? We differentiate this one. We differentiate this one time and put what? Put x equal xi in order to find out the value x equal xi plus 1, in order to find out the value of f dash xi plus xi minus epsilon, because this one is a true for xi minus 1 to xi. and if we try to write x lie between xi to xi plus 1, so here we replace I by the I plus 1, means fx equal 1 upon 6 hi plus 1 xi plus 1 minus x f mi plus x minus xi mi plus 1. In this way we update the function, and then we differentiate this function and putting x equal x plus xi plus epsilon and x equal xi minus epsilon, and if epsilon tends to 0, then we get what? Then we get this expression. After simplification we get this expression. So I am not going to derive this one, means by putting in f dash x between xi to xi minus 1, xi minus 1 to xi, we put x equal xi minus epsilon, and in fx defined for x equal xi to xi plus 1, we put x equal xi plus epsilon, and if we equate f of f dash xi minus epsilon equal to f dash xi plus epsilon, and if epsilon tends to 0, after simplification we get this result. So this one is a true for what? This one is a true for I equal 1 to n. I equal 1 to n. So if we closely observe this expression, that we obtain with the continuity of our function fx, continuity of a f dash x. So here how many number of unknowns? I equal to 1, if we put I equal to n, then m0 m1, I equal to 2, then m1 m2, I equal to n, then mn plus 1. So how many number of unknowns? There is a n plus 1 unknowns, and that unknown be the m0 m1 m2 and mn. So how many number of unknowns here? There is a n plus 1 unknowns, n plus 1 unknowns, n plus 1 unknown, n plus 1 unknown, and how many number of equation are there? There are n equation, because corresponding to I equal 1 we get a 1 equation, corresponding to I equal to 2 we get another equation, and corresponding to I equal to n we get the another equation, means we have a n plus 1 unknown, but how many number of equation? We have a n equation, we have a n equations. So how we find the value? Means how we find the number of unknowns? So here we use the concept of a what? Concept of a natural spline. What is the concept of a natural spline? In a natural spline, m0 equal to 0 and mn equal to 0, means a second derivative at the initial point of a cubic spline function equal to 0 and second derivative at a last point, at a end point equal to 0. With these this condition of a spline, be able to find out all the unknowns m0, m1, m2 up to mn. So once we find the values of m0, m1, m2, mn, and we put here the values of m0, m1, m2, m3 up to mn plus 1, basically here n plus 2, sir. I think n plus 2 unknown, not n plus 1, mn and mn plus 1 also. If we put I equal to n, then what will happen here? N plus 1 also, mn and mn plus 1, sorry. So there are n plus 2 unknowns, and with these two unknowns, n plus 2 unknowns, and how many number of equations? N equations. So I forget about this one. So this one is again we write here. Here if we write in this way. So how many number of unknowns? There is a mn and mn plus 1. So there is n plus 2 unknowns. N plus 2 unknown, and how many number of equation? n equation from, if we put I equal to 1, I equal to 2 and I equal to 3 up to I equal to n, and using the concept of a natural spline we get a 2 more equation. So total number of equation become n plus 2. There are n plus 2 equation and n plus 2 unknowns, then we able to solve n plus 2 equation and n plus 2 unknowns. With n plus 2 unknowns, then we able to find out all the n plus 2 unknowns. Once we find the values of m0, m1, m2, m3 up to mn plus 1, then we put these values here, then we get a desired cubic spline function for each polynomial. So what is the summary? Summary is here this one is a cubic spline function. So in order to solve a numerical problem, we need to remember this formula, fx equal to this one, and this one is a relation. This one is a relation between m0, m1, m2 up to mn plus 1. So there is a need to remember this formula also. Here hi plus 1 and hi with a class interval between first xi to xi minus 1 to xi to xi plus 1. So if this if there is a equal class interval, it's not necessary always there is a equal class interval, means you may fit cubic spline function for unequal class interval. That's why here we write hi and hi plus 1, means each class interval there is a different the difference of each class interval is a different. But if there is a same class interval, means hi equal to hi plus 1, means there is a equal class interval. If you try to fit a function, cubic spline function for equal class interval, then hi and hi plus 1 become h. And here also we write what? Here also we write hi equal to h. So after putting hi equal to h and hi plus 1 also equal to h, there is a need to remember this formula. If we remember this formula, means to solve a numerical problem, you need to remember this formula, these formulae. This one is a what? Cubic spline interpolation. Cubic spline function. Cubic spline function. So you need to remember this formula, fx equal 1 upon 6h, xi minus x whole cube, mi minus 1 and so on, and mi minus 1 plus 4 mi plus mi plus 1 equal to 6 upon h square fi plus 1 minus 2 fi plus fi minus 1, with condition of a natural spline. m0 equal to 0 means second derivative at x equal to x0 be the 0, and second derivative at x equal xn be the 0. So this one is a what? This one is a concept of a cubic spline function. This one is not a direct method, this one is a alternate approach. There is no need to directly find the values of a constant a1, b1, c1, d1, a2, b2, c2, d2 if we fit a polynomial a1 x cube plus b1 x square plus c1 x plus d1 for xi minus 1 to xi. So there is no need to directly find the values of these constants. That's why this one is known as alternate approach. In this approach, first we write a polynomial, first a first class interval, the second class interval, third class interval, and so on. So this one is a what? This one is a theoretical aspect of a cubic spline function. Means how we fit a cubic spline function in a different way.